Yet another video in our installment on common logs. In this video we want to use common logs to solve exponential equations. There's a couple ways we can do that. We can rewrite things into logarithmic form and then use our common logs to find values for those things. Or we can simply take the common log of both sides and see where that leads us. Taking the log of both sides is especially useful because it allows us to use the exponent property to drop things out of exponents and down in front. Okay, rewriting in logarithmic form might do some of the same things, but this will allow us to do it even if we have multiple exponents and things of that nature. So let's dive right in here. Let's take a look at 5 to the x equals 95, and let's see if we can figure out what x is. If we take 5 to the x equals 95 and we rewrite that in logarithmic form, we would say log base 5 of 95 equals x. And doing that now, we can see log base 5 of 95. Can't really do that, but we can use a change of base formula. So we can say the log of 95 over the log of 5 equals x, which means x equals 2.829. Now I had to plug that into my calculator to get that, but I don't have one that I can show you while I do it. So go ahead, pause, double check to make sure that you're getting the same thing. We have another way that we could do this. We could take 5 to the x and 95, and we could simply take the log of both sides. If we take the log of both sides, what that will then allow us to do is take this x exponent, drop it down in front, and we'll get an x log of 5 equals a log of 95. Divide both sides by the log of 5, and we will get the log of 95 over the log of 5. Exactly the same thing that we had just a minute ago over here. Okay, which gives you a little bit of inclination as to how some of these properties could be proved or shown to exist. And we would get the same value for x then, 2.829. This one will also work either way. I'm going to choose to do it with taking the log of both sides. First thing I'm going to do is I'm going to take the log of the 3 to the x squared side, and I'm going to take the log of the 21.5. Now, at any point in time, you can find, and we'll take our exponent and drop it down. At any point in time, since you have a log of 3 and a log of 21.5, you could punch these values into your graphic calculator, your scientific calculator, and get a decimal approximate. But that's all it's going to be at that point in time, is a decimal approximate. I like to wait as long as possible to do that. Okay, and we'll see that maybe in another example where we'll do it both ways. But when we do this, we can take and divide both sides by the log of 3. So we get a log of 21.5 divided by a log of 3. And then we'll take the square root of both sides. Now remember, when you take the square root, you have to take a plus or a minus a square root. So I'm going to simply plug in this whole mess into my scientific calculator, my graphic calculator actually, and find out that the log of 21.5 divided by the log of 3 and the square root of that mess is simply going to be an x equals a 1.671. Once again, we have a plus or minus. All right. Now, be careful with negatives. Remember, we're dealing with logarithms. We can't take the log of a negative number, but a negative here is not going to give us a problem. If you look at it real quick, we have our x value is going to be squared. So whether it's positive or negative, we're going to put it in there, we're going to square it, and that will give us a value that we're looking for. All right, a positive value. Do realize as you look back at this that you are squaring the exponent, you're not squaring the 3x. So you cannot multiply these two exponents. They are not both on the same base. Just a little something to be aware of as we go forward. I have two more examples, and this one I'd like to do two different ways. Actually the same way, but as we mentioned before, we can take the log of both sides. And as we do that, then we can drop this exponent down in front. So we'll get an x minus a 1 times a log of 7 equals a log of 5, and we can drop that x down in front as well. Forgot to do that. Now, as I do this, I'm simply going to keep that log of 7 and that log of 5. They are just numbers. I'm just going to use them as much as I can as just numbers. It means a little extra writing, but I'm going to distribute them, or distribute the log of 7, I should say. So x times the log of 7 and negative 1 times the log of 7 equals x log of 5. And I'm going to solve for x. And I don't forget about how I solve for x. I'm simply going to try and get all of my x values on one side. So we'll get an x log of 5 minus an x log of 7. And now I have a common factor of x that I can pull out right here. So we'll have a negative log of 7 equals an x log of 5 minus log of 7. And now to solve for x, all I need to do is take and divide both sides by that ugly mess that's next to the x. And this is what I have. Now, technically, this is my solution right here in its most exact form. That would be my solution. Negative log of 7 over log of 5 minus log of 7. And if I were looking for an exact value, that would be it. I'm looking for an approximated value, so I'm going to punch that into my calculator. I'm going to be very careful as I punch this into my calculator to make sure I put my denominator in parentheses. Remember, fraction bars are grouping symbols, and sometimes calculators don't realize that. And when I do that, I'll come out with a 5.783, rounded to 3 decimal places. And there's my answer. Now, another option here would be to take our log of 7 to the x minus 1 and equal that to our log of 5 to the x. Same way we started before. X minus 1 log of 7 equals our x log of 5. The other option here that we're going to look at real quick is to say, okay, what is this and what is this? We can put both of those into a calculator and get decimal approximates. And when I do that, I'm going to get a 0.845 for the log of 7. And I'm going to multiply that by my x minus 1, and I'm going to get a 0.699 for my log of 5, and I'll multiply that by my x. Now from here, it's just algebra. We just have some rounded values. 0.845x minus a 0.845 equals a 0.699x. And we can easily take and subtract 0.845x from both sides. So we got a 0.845 equals a 0.699x minus a 0.845x, or a negative 0.845 equals a negative 0.146x. So if we divide both sides by a negative 0.146, we get our answer. And our answer becomes an x equals 5.788. Now, you look at these, and they are mostly the same. Not entirely, though. Okay, we get as far as the 5.78, they stay the same. As we get beyond that, they get to be a little bit different. This one would be the one that I would consider more accurate. This one was built off of rounded values much earlier on. And those rounded values are going to have their effect as we multiply and divide. This is the last one I want to look at today, and we're going to look at it in two different ways. Partially because you could already do this one without our common logs, without logarithms at all, as a matter of fact. You could take the 16 and you could say, hey, that's a 4 squared to the x power. You can take the square root and say, hey, that's a half power. And from there, we can easily make this into a 4 to the 2x power and a 4 to the 1/2 x plus 3/2 power. Well, if I have the same base, what do we know about these exponents? Well, they have to make an equation as well. So we have a 1/2 x plus a 3/2, and if we subtract 1/2 x from both sides, 2 or 4/2, 4/2 minus 1/2 is 3/2 x equals a 3/2. Multiply both sides by a 2/3, and we will get x equals 1. So this one was able to be done without logarithms. But I want to look at this again. What if we were to look at it and approach it a little bit differently? What if we took 16 to the x equal to our 4 to the x plus 3 to the 1/2 power again, and rewrote the 4 to the 1/2 x plus 3/2 power. Probably don't want to get around that too much. Oops, exponent. 16 to the x. What if we were to take the log of both sides at this point in time? So we'll sneak a log in here, and we'll sneak a log in here, and now we have an x log of 16 equals a 1/2 x plus 3/2 log of 4. And from there you can see how this one's going to get just a little bit ugly as we take and probably distribute. I'm going to keep things as exact as possible in this one as well. So we'll have a 1/2 x log of 4 plus a 3/2 log of 4. And then we'll subtract this guy over to the other side. So we get an x log of 16 minus a 1/2 x log of 4 equals a 3/2 log of 4. Pull out our common factor of x. Give ourselves a log of 16 minus a 1/2 log of 4. Set that equal to a 3/2 log of 4. And now we can divide by that mess, and we'll get an x equals a 3/2 log of 4, all divided by a log of 16 minus a 1/2 log of 4. Now, if you punch that into your calculator, no surprise, you will get a 1 that way as well. Now in this case, yeah, we could do it both ways, and to be honest with you, I think in this particular case, that way is probably easier. However, what if I didn't have two bases that could easily be made into the same base? Well, the reason this worked is because as we took a look at our 16 and our 4, we could make these both into the same base and move on from there. What if I had like a 3 and a 5? What if I had a 2 and a 7? What if I had something that did not match up right? Well, now I'm going to be stuck going down this route. And once again, like we saw in the last problem, I could have gotten a decimal approximate here and a decimal approximate here for the log of 16 and the log of 4. But then after that, I will be dealing with estimated values. The estimated values are going to change the outcome by a little bit. How much is going to depend on how estimated they end up being. I like to keep things as accurate as possible, knowing that this is an exact value, and when I punch that into my calculator, I'm going to get as close to that exact value as I can. I hope this helps as you begin to solve equations using common logs, and check out our next videos, which will deal with natural logs.